Okay, let me set that my timer. Okay, so this is the entropy with respect to structure. And again, the more a molecule can twist and turn, that means that it can exist in more different states. So in this case, there is free rotation along the carbon-carbon bond. So this one here that doesn't have a carbon-carbon bond here, CH4, but CH2, CH3, CH3 has a carbon-carbon bond, and there's going to be rotation here that it can exist. And it takes very little to rotate it, energy, so there's going to be then different configurations. So the angle between the hydrogens on this side of the molecule with respect to the angles on that side of the molecule, they can be a lot, they can be, since they're turning, there can be many different states, and therefore there's going to be more states available for this molecule to exist than the CH4. In CH4, they are exactly 109 degrees here. These are 109 here too, but the angle between this hydrogen, let's say, and this hydrogen can be anywhere because it can be 180 degrees, it can be the same, can be 0, can be 90, because there's a rotation here. These hydrogens are going to be rotating around. And therefore it gives it more flexibility and larger number of states it can exist. Once you get to 3 carbons, the free rotation of the carbon-carbon bond allows them to actually have even more states, 270 as the value of entropy. If you have to 4, then again, there's more possible rotations, more possible states, more flexibility. So something that is flexible, it will have more different configurations, and the more flexible it is, the more different configurations is going to exist in, and the more the entropy that you can expect for those. And that is reflected on these numbers here for entropy that have been measured. So when we deal with a chemical reaction or a chemical system, then we are going to look at the change in entropy from between products and reactants. So the delta S of a reaction, where the reactants happen to be the system, meaning the chemicals that are in the chemical equation are going to be the system. Then the final is going to be the products, and the initial is going to be the reactants. Remember that in the equation we write reactants going into products. So this is the final, and this is going to be the initial state. So when then we can use the tables that we saw to calculate the delta S of any reaction, as long as we can go and look up the standard molar entropies on the table that we saw. So if we find those chemicals, and your book on the appendices on the back has a whole table of molar entropies, standard molar entropies, these values here. So what you need to remember is not only that it's products minus reactants, you also have to have the N, and N is going to be the coefficients. So these are coefficients in the balanced equation, in the balanced equation, the chemical equation, this kind is here. So do not forget to add those to your calculations. Okay, let's move along and let's do a practice exercise. So it says, using the values of Appendix 4, that's the appendix in the textbook, calculate the standard entropy change for the reaction. So Here we have the 4 components. So this is CO2, and these are the products, and these are the reactants, and their standard entropies. Remember that the units are going to be joules, mole, Kelvin, and this is Kelvin, so never use centigrades in your calculations because you're going to be going the wrong path and not get to the correct answer. And in multiple choice questions, I assure you, you can look all across the country, there's going to be the answer for people that use centigrades instead of Kelvin. So don't fall into that trap. Okay, so what we're going to do, we're going to do the sum of the N and then S zeros of products minus the sum and S0 of reactants. And that will give us the delta S for the reaction. So we're going to postulate that the delta S of the reaction is products minus reactants, final minus initial. And that's something that, since we're going to talk about delta H and delta S here, always when you say the delta of X, whatever is H or S or anything, or G, is going to always be the X final minus X initial. So this delta is final minus initial all the time. So don't forget that. Okay, so in this case, then the final is the product, initial are going to be the reactants, and we are going to calculate the delta S. Again, we're going to take the coefficients 4 and 6 for water and apply them to their entropies, 4 and 6, and these are the entropies from the table. Notice that we don't need to follow the units in this case, because it gets very cumbersome. You have to write a lot, and you're maybe you are more likely to make mistakes to follow the units. So just make sure that you actually, when you do this, then you have the correct units, but you don't need to put them into your calculations. So this is products, and then minus, and these are the reactants. And again, don't forget the coefficients. The coefficients are very important. 7 for oxygen, 2 for methane, no, ethane. And then you operate them. And again, another mistake that people do is just they put minus here and plus here, and they don't put these brackets. So they go minus this, and then they say, oh, this is adding. No, there's a bracket here, and there's another bracket here. So you need to operate within the parentheses or the brackets first, like we did here, and then do the subtraction. So this value is there. The value of 2 times 229 is here. Then you add this up as a single number, and then you subtract that single number. And when you operate, you'll get 619.4. This is telling you that the entropy has decreased, right? It's negative. Why has it decreased? It has to do with the entropy values themselves. Okay. Okay. And that brings us to Gibbs free energy, which I've been hinting of. And so let's go a little bit into it. So we have done this. We have done the delta S of the universe. The change in entropy of the universe is equal to the change of entropy of the system and the surroundings. Why? Because the universe, once you define the system, you're defining part of the universe, and the rest are going to be the surroundings. And this is going to be the system. So, and this whole thing, this whole big rectangle is the universe. So whatever happens in here plus whatever happens in the other part of the universe is the total universe, and that is the delta S of the universe. Now, the delta S for the surroundings, we found that we can calculate the delta H, that means how much heat is required, and divided by the temperature to calculate the delta S of the surroundings. So that's a useful equation. And if we multiply this equation by temperature, then we have T delta E, delta S of the universe is equal minus T delta S of the system plus delta H. I'm just questioning this because, so we are not going to use this equation that much. What we're going to use instead is going to be this one here, which says the delta G, the free energy, the one that we can use actually 100% of the time to predict spontaneity of a system gives free energy. And that is this equation, delta G is equal delta H, enthalpy minus temperature. Let me switch to the colors now. Because this is so pervasive that people forget. In Kelvin, minus T delta S. So the process can be endothermic or exothermic. If it's exothermic, that means this is going to be negative. And if the entropy increases, which is what usually brings you to a lower energy, so this is going to be, the energy increases, then this is going to be, if the entropy increases, it's going to be positive. So you have a positive. The temperature is in Kelvin, it's always positive. Because it's Kelvin, remember? And so this is going to, this whole thing minus T delta S is going to always be negative. And if the delta H is negative, then the delta G is going to be negative. Delta G is going to be less than 0. If it's less than 0, it's spontaneous. And those are the combination that do the two things that we have talked about so far, delta H and delta S. Delta H, if it's losing energy, means that the system is losing energy, and that is what makes sense. Again, in the half pipe, the ball will go downwards spontaneously because it's losing energy. So the system that loses energy is going to have a value, negative value for delta H. Let's say minus 0. I'm just going to take. So it's going to be negative. The entropy always tries to increase. So usually spontaneously means that the delta S is positive, means increasing. Why increasing? Because remember, this delta S means S final minus S initial. So if it has increased, that means that the S final has to be larger than the initial, otherwise it will not increase. And so if this is larger, if the final is larger than the initial, so then that means that SF minus S side, subtracting S side from S side, is going to be greater than 0. And so it's going to be positive. If it's positive and temperature is positive, that means that this part is going to be, once you have the negative sign in front of it, apply the negative sign, it's going to be subtracting from a negative number, and therefore it's going to give you a negative delta G, which is spontaneous. So, okay. So you had a table in one of the labs that it was talking about delta H and delta S. So you can review that again. I don't know if they have it. They probably have it in your textbook as well. Sorry, my voice is failing, and I should stop now and get to the Kahoot. So. Okay, so let's see if I can do it. No, I have already here, ready for you. So let me switch the sharing. I'm going to stop sharing my iPad. I'm going to switch the sharing to the where I have the Kahoot, which is this. I think is this one here. Okay, so and we're going to go into this. We're going to play this one. And I'm going to use in the classroom. Can everybody see can anyone confirm that you're seeing my screen with the Kahoot? It's starting to load.
Yeah, we can see it.
Thank you. Is it funny looking or not? Let me know if the lettering is too small. Let me change a little bit the aspect ratio to a more normal one. Okay, we need another three more players. Great. Anyone else? 34. And me is 35. So that's all of us. Perfect. Let's get started. Great. It is an exothermic process, and it is an exothermic process because I guess if you look at the word combustion means burning, and we know that anything that burns is going to produce a flame and is going to give off energy. And giving off energy means that is exothermic. So thermic means heat, exo means towards the outside, so it's bringing the heat from the inside of the chemicals towards the outside, the surroundings. And so that's how we can use this gas propane to actually cook. Propane gas is something that is sold as a combustible and a source of energy for heating and cooking. Okay, good. Let's go to the next one. Right, a combustion reaction is a reaction with oxygen. So you see here you have propane gas, and then you have oxygen. And oxygen actually goes into the carbon and into the hydrogen. So the carbon, once it gets oxygenated, goes to CO2. The hydrogen, once it gets oxygenated, gets into water. So correct. So hydrogen and carbon atoms are forming new bonds with oxygen. So these guys here are combining with the oxygen that we need. So if we take the oxygen out of a combustion, we stop this reaction. because the reaction will not occur. There's no oxygen to combine with carbon or hydrogen. Good. Good. Let's get to the next one. Great. So the correct answer is an endothermic process. And the fact that you think it's an exothermic process, it might not be your personal fault, but the fault of the instructor who taught you chemistry before. And this is a common thing that we instructors say. We store energy in bonds, and that is so wrong. And so when I put this question up, I always see this pattern. At least equal amounts of people will choose the wrong one. Think about anything that you break. So you have a piece of glass or anything you want to break. What do you have to do to break it? You have to apply force, right? You have to make those molecules that are making whatever, the glass or the cup or the phone, the phone you're trying to break, you want them to come apart. You want to break the bonds, and that requires energy. So something that is bonding, it has a force that is keeping those atoms together. And if you want to pull them apart, you need to overcome the force that is keeping those atoms together. So when you did Lewis structures, you put electrons that are being shared, and those electrons are keeping those two atoms together. So if you want to pull them apart, you need to put energy. And if you need to put energy, that means that the system has to gain energy. So the system gaining energy means it's an endothermic process. When you form bonds, is the reverse process. Okay, so remember that for breaking bonds, you have to actually put energy in. So, okay, let's go to the next one. Great. So yes, so most of you got the message. Yes, so the bonds, when they form, they actually release energy. So to me, when they say, oh, that you store energy in bonds, no, when you form a bond, you're releasing energy because you're going again downwards, the half pipe. You're releasing the energy to get to a more stable state. Otherwise, the bonding will not happen spontaneously, and bonding happens spontaneously. So good job. Okay, so delta H is, again, finals when it's minus initial. If something is giving off energy, right? Combustions give off energy. That's how you heat your house. That's how you cook, by actually heating up your food. So there has to be a source of heat. And so if you're using gas, like I do in your stove, you are burning propane or propane gas and and releasing the energy. So final minus initial means that the final amount of energy or enthalpy of the system has to be less than the initial one. That way you can release the energy. So releasing energy is just like your bank account. If you're releasing money out of your bank account, that is a negative to your balance. So the delta H is like the balance. So all the H is like the balance. The delta H is going to be negative because you are releasing energy. Okay, so do not get confused with that. Good. Next. Good. So all of you know your gases. Okay, so that's a good start. Great. These are the states of entropy that we're talking about. Good. So the largest will be C, the gas phase, where you have most of the molecules spread throughout the container, and they can exist in a lot of different positions, a lot of different states. Great. Let's go to the next one. Good. It's only atoms that have only vibrational but no translational motions. So I think no, bromine will have translational motions because bromine is a liquid. So the right answer was red, only copper. I don't know why I had that, only bromine. Well, let me read again the question. The atoms that have only vibrational, no translational motions. So yeah, so bromine is a liquid and it can go. So let's go back to the figure here. So again, you had a solid of copper. You can see the structure or their structure. These are the molecules of bromine, which is a liquid, and this one is a gas. So the ones that can only have vibrational and not translational are going to be the copper. Remember that the liquid goes to the bottom of the container, and therefore there is motion. Otherwise, it would not take the shape of the container. Okay, so the correct answer is 6, or the 6 that mentioned only copper. I'll have to go back and fix that. Oops, sorry, I double clicked too quick. Ooh, there's a split here. Okay, so the ones that can have vibrational, translational, and rotational are going to be the ones that have helium and bromine. So only helium, no. Helium has vibration, translation, and rotational, and so does the liquid. So translation means that they can move around. Rotational means they can spin around. And liquids can spin around and move around, but they just move at a lower speeds than the corresponding gas phase. So the correct answer is the blue one, only helium and bromine, both of them. Okay, so let's get to the next one. Wow, okay. Correct. It increases because, again, you'll have a larger number of possible states in which this can happen. So here you have them ordered in columns, 2 columns blue, 2 columns red, and then it's going into not so much ordered. So again, to use the disordered picture of that you might have learned before if you have taken chemistry and talked about entropy, this, the one to the right is more disordered, the one to the left is more ordered. But what I would like you to think about is the number of states. So the red, instead of being where they are, they could be in other positions as well. It depends on how the molecules start to collide and grow apart. So there's more possible states in which these molecules can exist. In the case of the one on the left, this is typical of a solid. So this is not a gas nor a liquid, it's a solid. And it looks like it's melting into a liquid. So that means that the number of possible configurations for the solid part is going to be mostly just vibrations within these atoms here. These represent atoms. The ones on the left, they are free from one another. That means that they could be in different places and therefore more possible states. And that's what entropy is about. How many possible states can that substance exist in? So good. So most of you got it correct. Congratulations. Good. Good. Congratulations to everyone. And there's number 4 and 5. Great. So give me some feedback if you can, and we can wrap this session today. Any questions or comments? Great. So if there are no questions or comments, then we can call it a day. Unless someone would like to ask.